Up to now, we discussed the fundamentals of topology optimization, but right now we started discussing the details of this optimization methods. Now, if you remember in the previous part, we said that we have a kind of a discrete domain, and we are trying to find a way to fill these finite elements. And how we are going to do that? Now we are going to discuss such details in this chapter. And we are trying to find a proper way to distribute these materials, and we may again make use of some stiffness tensors. Here you see the equation about them, and we have two cases. In the first case, we may have material in elements. For instance, this might be filled with material, and we may not have any material in the, let's say, such finite elements. And for such cases, this value is equal to 0, but if you have material, obviously, it should be equal to 1. And we have an E0. This is actually the properties of isotropic material for a single element. And if you have material, you need to multiply with 1. But if you don't have any material, then you can simply multiply with 0, and then your stiffness tensor will be equal to 0. Another thing is that since we start with an available material, we have a constraint on the volume of the material. So we have this amount of material to be distributed into the finite elements. Now we have again a discrete design problem, and we are trying to find the cells which contain material and the cells actually which has no material. And to come up with such solutions, we need to have a kind of a penalty so that any intermediate density will be steered to the 0 or 1, so that we don't want to have any intermediate density values in elements. Since it's not possible whether you can put material there or remove material. We cannot have any elements having, let's say, 0.5 density value. It's not possible. And we try to find actually a continuous function so that this optimization will be done in an analytical manner, but it's not quite possible. We need to, that's why actually have new formulations, do discretization and try to solve it in a much simpler way. And in our case, actually, the design variable is density. We will be adding some kind of penalization on density so that in the iterations, this density value will be steered to 0 or 1. These are things we mentioned. We may have intermediate values of densities, but since in real life, in practice, it's not possible to have intermediate density, so that's why we will be trying to find ways to penalize such densities. And the most popular way to do is continue with solid isotropic material with penalization method. This is called as Siamp method and quite popular these days. A very efficient one. Its time complexity is not much, and in maybe less than a minute, you can find a solution to some simple problems. But obviously, for complicated shapes, you may need to work for some hours on a typical computer. Let's go back to our formalization. And we said that we are looking for a continuous function, and so that it will be our design variable, and that is, as we discussed, the density of the elements. And here we have this penalization factor. This is the power of the density function. This is density of a specific cell, and P should be higher than 1. Why is that? Since if P is less than 1 and the density value is ranging in between 0 and 1, since if your value is in between 0 and 1, let's say if you have 0.8 and if you have some kind of power, let's say greater than 1, 2, then this will be 0.64. As you see, this is decreasing and it's steering towards 0. That's why we want to have powers greater than 1. But if you have less than 1, then that will not be the case. You will not be able to steer the densities. Obviously, rho of x is our design function, and E0 is the material properties of an isotropic material. So this is our kind of constant. And then depending on the density, initial density, we try to do some optimization. It will be changing in between these values. Sorry. So as we said, we prefer to have densities greater than 1. So the penalization factor greater than, so that any intermediate dense or unfavorable values will be eliminated. We either have zero material or full of material about these elements. And this is actually named as an implicit penalization. We don't have any explicit penalization, like for instance, if density is equal to some value, do this penalization. We don't have such explicit penalizations. We have an implicit one, and this is done with the help of the penalization factor P, penalization power, we can say maybe. So what about intermediate values, intermediate density values? Is it possible? And if you have a kind of an composite material, that might be possible for some intermediate values. You can have some specific lattice structures and try to obtain such densities so that you may not need to have a power greater than 1. The reason we are using P greater than 1 is that in practice, we cannot have such intermediate densities in an easier way, but maybe in upcoming years that might be possible, especially with additive manufacturing. Now let's go into some other details related with the Siamp method, and you can realize this method if with materials in practice if you satisfy these equations. If you are doing the optimization in 2D, then this should be satisfied. Your power, your penalization factor should be the result of this function. It should be at least greater than the maximum of this pair. And for 3D, we have a similar one, but this time the numerators and denominators are different. And according to numerical analysis, for 2D, P should be at least 3 so that we can have a Poisson ratio of 1/3. And for 3D applications, for 3D optimization, again, P is not 1, it's at least it should be 2, but for most of the cases, better you choose P as at least equal to 3. Now we will discuss some alternative ways to solve this problem. Otherwise, it's quite difficult. We will look for some alternative reformulation of the same optimization problem so that the computation will be much easier. So for the first one, actually, we will be discussing a minimum compliance problem. And for this, we have some computational efficient approaches. And we'll be using mainly minimum potential energy. By using this energy equation, we will be actually decreasing the time complexity and have better solutions with this approach. And now let's have a look at this equation. This is actually this function, and we will be working on this function. And this is in here, U is the displacement field, and L, if you remember, is the forces we have on it. And we are trying to minimize the energy, minimize the potential energy, so that our part will be stationary, the finite elements will not be moving. And at the equilibrium, while our part is actually stationary, this equation, this inequalities should be satisfied. -1 or 2 of L of U should be less than 0. And we can represent this problem in a different way like this one. We are trying to minimize the potential energy. Or if you want to formulate the same problem in terms of stresses, that will be the expression. And in that expression, we have the compliance tensor instead of stiffness tensor. This time we are using compliance tensor. And here we have actually stresses. While we are trying to minimize stresses, it should be belonging to an admissible stress field. And actually, if the field is known in this optimized structure, then you can have a kind of an optimal distribution of the stiffness so that your strain energy is this time maximized. And this is very important. Why in the design problem, if you come up with such a case, then you can need to distribute the material and have strain energy maximized. Now let's have a look at some solution methods, what type of steps we should follow in the Siamp method. We are going to actually use a kind of an interpolation in this method. It will be a kind of sizing problem over a fixed domain. So at the beginning of the problem, we have the domain, we have some constraints, boundary conditions, some loads. These are all fixed at the beginning. And then from iteration to iteration, we'll be modifying the material properties of these sets, whether they are going to have material or not. And while we are actually employing this method, we should find an efficient way. We shouldn't be consuming too much time. So that's why we will be actually working on these optimization settings so that things will be much easier for us. And there needs to be actually some conditions for optimality. Otherwise, you cannot come up with an optimum solution. And these are some kind of power parameters or density values. We need to be checking, we need to be updating these densities so that it's always an optimum distribution. So now let's go back to our formulation once again. So this is our bilinear energy form. We have the stiffness tensors, and this stiffness tensors are actually depending on density function, penalization factor, initial, or the stiffness of our, let's say, isotropic material. We have the volume constraints, and our densities should be in between 0 and 1. And in between iteration steps, we are actually doing some kind of computation to determine the new density value for a specific element. And this time, with the help of language multipliers, we have some parameters here. I'm not going to discuss all the details that are available in some specific papers. If you are interested, you can have a look at them. But right now, we can take them as granted. These are kind of multipliers for the next iteration. So as you see, the density of an element, the density of the element for the next iteration is equal to one of these. Depending on these values, we should follow any of three and obtain the new density value for the next design. And here actually, in this multiplication or computation, we are trying to find whether whether there will be more material in the cell, in the same cell, or less material. And in that equations, if you have realized, we have some parameters. These are tuning parameter and a move limit. Eta is the tuning parameter, and zeta is the move limit. And with the help of them, you can control what is changing in between these steps, in between these designs. And you can adjust them to have more efficient methods. So obviously, the density of the next design depends on the current density value and the language multiplier lambda. And again, it should be adjusted properly so that you'll come up with an optimum solution. And at the beginning, the volume might be decreasing very much. It depends on which steps are you on actually in this optimization. If you're to the end of this optimization, then probably there will be less change, but at the beginning, we expect to see much changes. And in order to determine the value of lambda, we may use bisection methods or another Newton method. So this is actually kind of an implementation approach. It's up to you. There are papers, there are studies using different methods. And for typical values, these are for eta 0.5 and for zeta is 0.2. And actually, the most effective way of this Siamp method is that each design variable is actually updated independent from the other elements. So it's a nice feature, and that's why actually we prefer to use Siamp for most of the time in topology optimization problems. And obviously, it's not that easy. We have many sub-steps, and at each sub-step, we need to use the best method, the most efficient method, so that it will take less time and the output of that specific step will be as correct as possible. And at some of these steps, you may be using mathematical programming to have, again, better results. Let's discuss the implementation, how we are going to implement this Optimality criteria method. And we will be distributing this material, as you know, into these cells, into these elements, so that they are all optimum. And at the end of this optimization, we don't want to have any intermediate values. We're going to penalize them so that there will be cells having no material and cells with full material. What are the steps in these implementation? First of all, we do a kind of a pre-processing of geometry and loading, which means that you define the geometry, you define the loads, whether you have distributed or point loads, you define boundary conditions, and then do the optimization. And lastly, you can do some post-processing. If you have some non-manifold regions, you can modify, you can have extra cells so that it will be possible to fabricate the resulting design. So what we have in the pre-processing of geometry and loading, first of all, we need to have a domain. So we need to define the fixed parts and body forces, surface traction. So they are all defined in this part. And at the below image, as you see, we might have some fixed void regions and fixed solid regions. They are all defined at the beginning of this optimization. And then once you are done with definitions, then you need to construct a finite element mesh, which will be the same throughout this optimization. You cannot change it at an intermediate step of your optimization. And it should be as fine as possible so that you'll have much better optimization. But obviously, if you increase the number of elements, your optimization will take more time. And we will be obviously using the same finite element meshes for the fields and for the displacements or all other things. You cannot have 2 different or 3 different meshes. Single meshes is fine for all the variables. And in the optimization, what we are doing, we will be using some kind of finite element analysis. Since we already have the finite elements, we can perform analysis on them and try to find their deflections, their stress values. But in this optimization, the most important is the displacement of these finite elements. So at the beginning of the initial optimization, we have an initial design. What we do, we distribute the material in a homogeneous way. So let's say if this is our cantilever beam, and let's say this problem is that at the end of this optimization, you can only use half of your overall volume. So what we do is that at the beginning of the optimization, we distribute our material into these finite elements such that the resulting amount of volume will be equal to the 0.5 times the whole volume. So the simplest thing is to have densities of 0.5 in each cell. So this is how we do the homogeneous distribution of our material. And then for this distribution, we do some finite element analysis, and we determine the strains, the displacements, and obtain the compliance of the design. And if you're not happy with it, then you need to do some update on the density values by using language multipliers. For instance, this might be in the next step, might be increased to 0.7, and this might be decreased to 0.3. So it depends on the critical steps of the optimization. And then once you have it, then you repeat these steps, do another finite element analysis, get another result, and check if it is fine or not, and go on with the, if it's not fine, you can go on with the next design. But at some point, you will realize that there will be no marginal improvement in terms of the compliance. If that's the case, then you can stop and tell the user that, yes, this is the optimized design, and we cannot, it's better we not do more computation since the compliance is not changing anymore. These are things I mentioned. Okay, so we do these steps until we come up with an optimal design. And you should be also careful about fixed regions. You may have some regions with material and some regions with no material. You should be aware of all these and try to employ actually this limitation on your next iterations. And later, after you are done with optimization, you can do some post-processing, have kind of smoother borders. It's up to you. You may just prefer to go with the result of the optimization directly, but it's better you do some post-processing according to your fabrication technology. So these are things we discussed. Yes, let's have a look at discuss a little bit the power P. What happens if you, for instance, keep P is equal to 1? We said that it's better you keep it maybe higher than 3, but sometimes you may actually set it to 1. At the end of this optimization, you may come up with some regions having gray color, which means that they will have a density of 0.5. Since we are not doing a penalization, if P is 1, at the end of the optimization, it's highly probable that we will have regions with intermediate densities. And again, if your manufacturing technology machine is capable of actually fabricating such cells, such elements, then you can go with that. But if you are doing some machining or other conventional manufacturing technologies, then it's better you go with P greater than 3 and don't have any gray regions.